Hi everyone, and welcome to Erik's Electronics Workbench and part 2 of the NAD C356BEE integrated amplifier repair. If you haven't seen part 1, definitely check that video out to see the troubleshooting that I did to get to this point. You'll see a link to part 1 in the description. The new components have arrived, so I'll get started on installing them. Then I'll show how to check several adjustments such as idle current, the ISC or Impedance Sensing Circuit, and minimum volume adjustment. We'll also take a look at the clipping circuit to make sure it's working since all the active components have been replaced. And of course a full power output test on the amp. NAD uses what they call Power Drive in this amp, and quite a few other amplifier models. If you're curious about how that circuit works, stick around, I'll go over those details as well. So lots of information in this video to help you if you're servicing this model amplifier or one similar to it. So quite a bit to do, let's get started. You may have heard NAD pronounced as NAD. An online search only reveals a debate as to which way is correct, although the preference seems to lean to NAD. So I thought the best way to figure this out would be to go direct to the manufacturer and ask them. I reached out to the customer support department and promptly received a reply from Mark. He confirms the name is pronounced as NAD, the complete name being NAD Electronics International. The letters are actually taken from the words New Acoustics Dimension. Alright, all the new components have arrived, so I have the capacitors, resistors, transistors, and the Zener diodes. Now I've ordered a few extras of each component. It's a good way to stock up, and I'll often do that when I'm ordering parts. And for example, I didn't have any of these 20-volt Zeners on hand, so now's a good time to get a few extras. Now these were purchased from Mouser Electronics, and Mouser is one of my main go-to sources for electronic parts and components. Mouser is in no way a sponsor of the video, again just one of my main sources that I do use. And Mouser has a very strict quality assurance program, so there's a lot of fake components on the market, so be aware of that. So when you order from Mouser, you know that, for example, the transistors that you're getting are definitely the genuine originals and not some type of a fake. I also use DigiKey. There's many other sources out there as well, but make sure that the parts that you're ordering are, original and what they're purported to be, because if they're not, you're definitely going to have some failures and problems. Now, as I had mentioned in the part 1 video, there were several resistors in this amplifier that look to be too small. They appear to be half watt in size, and the schematic calls them out as 1 watt. So I wanted to replace them. Now, this resistor right here, for example, is a 1 watt rating. And let me get this touched up a little bit here, you can see that. So take a look here, these are 82 ohm 1 watt. And notice they're also metal oxide, which is exactly what the originals are. So I can definitely confirm that the physical size of this resistor is larger than what's in the amplifier. So someone probably has been into this amp and maybe attempted to repair, would be my guess, and maybe used the wrong value of resistor. But a half watt rating resistor in a place where a 1 watt resistor should be is just a failure waiting to happen. So good to get those replaced. Now also going back to that metal oxide type, when you're replacing resistors, make sure to go with the correct type. Metal oxide resistors are often used in power handling applications. They're also flame proof, which is an important feature. You wouldn't want to use something like a carbon composition resistor in that position. And when you're replacing the capacitors, keep in mind the voltage ratings. You want to go with an equal or higher voltage rating, within reason of course, and the physical size of the capacitor, the lead spacing. Make sure you take measurements so that the components will fit on the board the way you expect. And don't change the capacitance value unless you know what effect it would have on the circuit. If you're working on something that's very old, that has non-standard values, that you might come across something that say is a half microfarad, and a modern value would be a 0.47 microfarad, and that's perfectly fine to substitute that way. But in a modern piece of equipment like this, all the components are standard in value. And one other thing was on the transistors, I noticed on the original part numbers, after the part number, it had the letters GR. And it's really important. GR is the HFE range, or the gain of the transistor. And there's different ranges, at least on these part numbers, that are available. So these replacements are also the GR type, and that's actually the highest HFE range. And I have some extras, and I'm going to try and match these as close as possible within the groups that I have here. It's not super critical to match, but I like to do that when possible. But again, these are the GR range for the HFE values. All right, so I'll get started installing all of these components, and then we'll move on to doing the testing. So when you're installing electrolytic capacitors, pay close attention to the polarity markings on the capacitor and on the circuit board, because if you install an electrolytic capacitor backwards, meaning that the polarity is reversed, they'll quickly fail and oftentimes they'll explode. You definitely don't want that. So just as an example, here's an electrolytic capacitor. And you can see the negative mark right there. So the standard way is that the negative side is marked and the positive side is not marked. And then the negative lead is cut shorter than the positive lead, but you shouldn't just rely on the lead length, always go by the marking on the body of the capacitor. So on this particular circuit board, the negative side on the circuit board silkscreen is marked by the shaded side. And it's typical that the negative side is marked on circuit boards, but there's no standardization. So you might find that the positive side is marked. Sometimes both sides are marked. And on some boards that don't have a silkscreen or have poor markings, then there is no marking whatsoever. And in that case, what I typically do is take a Sharpie pen and put a little dot next to the negative side before I remove the capacitor. And that way, when you go to reinstall the capacitor, there's no confusion. It can save a lot of trouble later on. Now, there are non-polarized types of electrolytic capacitors, and in that case, of course, it doesn't matter which way they're installed in the circuit. And you can tell a non-polarized capacitor because they'll often be marked as NP, or of course, they simply just don't have any polarizing marks on them. And in that case, it doesn't matter which way that you install them in the circuit. These are the transistors to choose from for the soft clipping circuit. So I ordered more transistors than are needed for the repair, but by doing so I can go through and pick the two closest matched pairs. If I ordered exactly the number needed for the repair, then the chance of getting those matched pairs would be pretty slim. So the soft clipping circuit is located right at the input of the power amp section, and the job of the soft clipping circuit is to limit audio signals that are so high in amplitude as to cause clipping in the power amp. So I want to know that that circuit is working the best that it possibly can, and I think that matching these transistors is a good idea. So by matching them, I mean that the HFE, or the beta of the transistors, is as close as possible. So I used my transistor tester, and I took the measurements, and you can see they're written down the side right here and over here. So these are NPN, the 2SC 1815, and the PNP type is the 2SA 1015. And the GR after the part number is the HFE range. I don't have the data sheet in front of me, but I know that the GR is the highest range. I think it goes from 200 to 400. So you do have some variation that's normal within the HFE of the transistors. But again, that GR is the highest range. And the transistors I removed from the circuit were also marked as the GR. So there are two other HFE ranges of these transistors, and they're all lower, of course. So for the circuit to work correctly, you do want to use that correct range. So we have an exact match right here. You can see it's 288 and 288, so that looks perfect. And 286 and 283 will be another very close match. So no problem using that. You can see the others, 308, 279, some of the other numbers start to drift apart a little bit. And of course, we're matching from the NPN to the PNP. These are complementary transistors. We're not matching within the NPN. In some circuits, if you were, let's say the transistors are paralleled and they're sharing the current, you might want to match, within a group of transistors, but that's a whole different type of circuit. So again, here we're just matching for the pairs of transistors. All right, so all the components have been replaced in the soft clipping circuit. I've also replaced all the electrolytic capacitors that are near the heat-producing components, and I mentioned wanting to do that at the end of the part 1 video, so that's been taken care of now. And 2 of those electrolytic capacitors are in this soft clipping circuit. So I started taking some measurements around the soft clipping circuit regarding the DC voltages and resistances, just to make sure that the circuit looked okay, given the problems that had occurred in that circuit. And I started to realize that particularly the resistance readings were not matching the schematic. So I thought, is there a problem? What's going on here? Now, when all the active components in the soft clipping circuit were removed, I took that opportunity to take some measurements around the remaining resistors, and all the resistors checked out okay. So I felt that they were perfectly fine. None looked overheated. The values were spot on. I didn't see any problems. So I was really surprised that these readings were not matching the schematic. And then I realized the schematic actually has an error on it. So before we look at the schematic, let me show you 2 different resistance readings, and then we'll go over to the schematic. So right now you can see these probes are just touching on the board. I've got them poked in right now, and I'll show you on the schematic where I'm taking this reading. But right now you can see it says 2.6 k ohms, all right? And the switch on the back panel for the clipping circuit is in the on position right now, okay? So when it's turned on, we have 2.6 k ohms. So I'm going to reach around back here and turn the switch off now. Okay, so now the soft clipping switch is turned off, and you can see it jumps up 5.15, so you could almost call that 5.2 k ohms, very close to that value. So now let's go over to the schematic and take a look at where the mistake is at. All right, here's the portion of the schematic that shows the soft clipping circuit, so let's take a closer look. So the actual problem is that this half of the switch over here is drawn incorrectly. It should be drawn this way, and I'll explain a little bit more. Now, the part of the switch that's on the left side is drawn correctly, and this half of the switch over here controls the front panel LED. So on the LED, the anode is connected to a positive voltage supply. The cathode comes over here to the center point on the switch. You can see it also jumps up to this top position, but that really has no purpose because you'll see in just a moment what happens. So these two bars on the switch right here are mechanically linked together, and what it's doing is electrically in the on position, it's taking this center position of the switch and connecting it to this lower terminal, which of course grounds the cathode of the LED and turns it on. Now when the switch is moved to the off position, this bar moves up and it's just taking this center point and connecting it to the top, which is already linked together. Nothing happens, the LED stays off. So of course that works exactly as expected. But on the other side of the switch, again, the bar is electrically tying the center point to this bottom point, and you can see they also have them jump together, so really nothing's happening there, which means this part of the circuit coming over here goes nowhere, and this part of the circuit comes over here, it goes nowhere. Well, that's not actually how the readings reflect this actually functioning. It actually works the way I've redrawn it over here. So you can see this part of the switch, this point right here comes down, that's this point right here is this point here. So let's take a look at how it's drawn originally, and we'll compare it to what happens, the way that I see it actually working. So we have four resistors right here. Each one is 1.3 k ohms, okay? Now, as you remember, when the switch on the back panel was in the on position, we were seeing 2.6 k ohms on the digital multimeter. So let's assume this position, or the way it's drawn originally. If this is in the on position, this point here goes nowhere, this point goes nowhere. We have 4 resistors in series. Now the digital multimeter's probes were connected right here and right here, okay? Now these are very high value resistors, and we have diodes over here, so we can basically neglect the effects over here, and this is 100 ohm and into the base of the transistors, and it was not turning the transistors on in the resistance mode. So we're just looking at the resistance right here, and as I mentioned, these capacitors have already been replaced. So there's no issues going on with that part of the circuit. Well, again, we were seeing in the on position of the switch 2.6 k ohms. So from here, if you have 2.6 k ohms, but these are all in series, again, going by how the switch is drawn, electrically that doesn't work. It does work if you draw it this way. So the way I've redrawn it, in the on position, you have the bottom part of the switch linked to the center and then jumped up to the top, and that would electrically, in the on position, tie this point to this point, effectively shorting these two resistors out. So now you have a 1.3 k ohm in series with a 1.3 k ohm. Okay, again, these two resistors would be out of the circuit. And 1.3 k ohms times 2, of course, is 2.6 k ohms, exactly what we were seeing. So the switch must be working this way. Again, this is drawn incorrectly. And then going to the other position, if this is opened up, that's when this part of the circuit, has all 4 resistors in series. So in the off position, all 4 in series, of course, is 5.2 k ohms, and we were seeing very, very close to that value. So if you're troubleshooting this part of the circuit, remember, this is how the switch should be drawn. These components that I have little red marks next to are all of the components that were replaced. So as I mentioned in the part 1 video, I found 2 resistors that look to be undersized for their watt rating. So the schematic calls them out as 1 watt resistors, but to my eye they look like half watt resistors, and both were installed on the right channel. So one of them is an 82 ohm resistor and the other is a 10 ohm resistor. Now the same 2 resistors appear in the left channel, and they look perfectly fine. I don't see any problem with their physical size. They look like 1 watt resistors, and it makes sense that they should be the same between both channels because of course the circuits are identical. So I'm not sure what was going on the right channel. Maybe they were replaced by someone. I don't know if the manufacturer decided that a half watt rating was okay to use. Why would they change, halfway through the production, one channel is 1 watt, the other channel has half watt. That really doesn't make sense. So, maybe they were replaced at some point. But nonetheless, you can see right here, this is the 82 ohm resistor that I removed, and this is the new 82 ohm resistor that's 1 watt. You can clearly see its larger, physical size. So this must be a half watt resistor. And this is the 10 ohm 1 watt resistor. So I'll get those replaced and we'll continue on. So at this point, all the components that needed to be replaced have been taken care of. And I've had the amplifier turned on for about 20 minutes now, and it has not gone into the protection mode. So all the issues that we were seeing in the part 1 video look like they've been taken care of. So that's very good news. We can move on to some other adjustments and then testing the performance of the amplifier. So when you're making the idle current adjustment, it's really the same on any amplifier. The procedure is the same, and it's pretty straightforward to do. So I'll just kind of highlight some of the main things to keep in mind here. So the first thing that you need is a very accurate digital multimeter. You could use an analog volt-ohm meter as long as the scale is appropriate and it's able to read very low voltages. You can see this is 6.1 millivolts DC. So again, you need an accurate meter, something that is good down to those very low values. Now the other thing to keep in mind is the test probes that you use. I find it very convenient to have test probes that have little clips on the end so they can actually clip into the circuit and you don't have to hold them in place. Really two reasons for that. It makes a good electrical connection. You're dealing with very low voltages, so any kind of intermittent or iffy connection, those low value readings here are going to be all over the place. But the other thing is that the idle current is not something that you make very quickly and just turn things on and dial it in and walk away. It takes some time, so the amplifier really needs to be turned on for at least an hour or so, and it needs to come to thermal equilibrium, and you need to monitor that voltage. So you don't want to be standing here with the probes, touching in and holding things that long. And sometimes the test points are not at actual pins that this has. Sometimes it's actual component leads. You might be clipping on a resistor or a transistor's lead, something like that. So again, having clips that go into the circuit like this is convenient. It can also keep you from slipping and causing a short circuit. Definitely not something that you want to do. The output stage has considerably high voltage all around it, so you don't want to cause any short circuits. Now, the other thing to keep in mind is that you don't want any audio signal going in and nothing connected to the outputs. So there's absolutely nothing connected to the amplifier. That would affect the readings, and if you have an audio signal going into the amplifier and you measure at these points, this is going to be jumping all over the place, which is perfectly normal, but that's no good when you're trying to make this adjustment. So again, no signal going in, nothing connected to the output. And of course, if you're following along, you're definitely doing so at your own risk. Just keep in mind, again, that there are high voltages in an amplifier like this. On this amplifier, each output stage rail voltage is 55 volts, so plus 55, minus 55. And of course, it's necessary to have the amplifier turned on when you're doing this test. So, there is high voltage exposed in here. So with two 55 volt rails, you have 110 volts, not something you want to come in contact with. So take care and be safe. You're definitely doing so at your own risk if you're following along and working on an amplifier like this. All right, so let's take a quick look at the schematic for this particular amplifier. So this is just the left channel section that's enlarged. So you can see that the idle current adjustment we're looking for is 6 millivolts. So yes, it is a current, but we're measuring it as a voltage because there's two resistors right here, very low ohm resistors. They're only 0.068 ohms. But the test point right here and right here means that we're just basically getting a voltage drop across these resistors, and that's what we're actually measuring. Now, in some amplifiers, you're actually measuring the voltage drop on just one of these resistors, so it's always important to know the voltage that's given. Where are the actual test points? Is it across both resistors or just one of the resistors? So keep that in mind. This center point right here is the positive output going to the speaker terminal. Now the adjustment is actually over here. You can see this amplifier has two variable resistors. Most amplifiers only have one, and the adjustment's usually pretty touchy, so you don't come in here and turn things a half or 3/4 of a turn. It's just very, very minor adjustments, and then watch for the change and readjust as needed, let things stabilize. So definitely take your time when you're doing these idle adjustments. Now, again, this amplifier has these two adjustments. One's a fine control, one's a coarse control, which is a nice feature to have two adjustments. But again, the procedure is the same whether you have one or two of these potentiometers here. Okay, so this is, of course, the left channel. The right channel is absolutely identical. So what I will do is let this sit here for at least an hour or so and monitor that voltage. When I turned the amplifier on, it was around 7 millivolts, so it's already come down and stabilized pretty close to 6.1 millivolts, which is really, that's perfectly fine. I'd be happy with that value. The 6 millivolts it's given, you should be close to that, but it's always going to fluctuate some. So when this channel looks like it's stabilized and I'm happy with it, I'll just move on to the other channel, make any adjustments if necessary, and then we'll move on. All right, here we are on the right channel's idle current adjustment test points. You can see it's basically sitting at about 6.2 millivolts, so looks perfectly fine. I don't see any issues with that. And keep in mind, 0.2 millivolts is just 200 microvolts away from the ideal value, so very, very close. I haven't made any adjustments on this channel. It's exactly the way it was when I connected the test probes, so I'm inclined to leave things just the way they are on this channel. Now, keep in mind that it's normal to see these voltage values fluctuate some within reason, and one of the things that can cause them to fluctuate is line voltage variations. So on my bench here in North America, it's 120 volts, and the line is quite stable. It really doesn't vary all that much. But if you're in a location where you have considerable line voltage variations and you're trying to do this adjustment, you might notice that the values are kind of hunting around considerably and you can't get it to stabilize. You might consider using a variac to stabilize the line, but use it, within reason. If it's just a few, volts up and down on the line, probably not a big deal. But if it's wide variations, it might help out. But again, if you're using it to try and correct for just, a little volt here and a couple of volts there kind of thing, you're going to be there all day making adjustments and just kind of going in circles. It can be very frustrating. So I wouldn't recommend it in most cases, but again, it might help out if the line is, varying considerably. So you might be asking, what actually happens if the idle current is too high or too low? So let's take a quick look at the schematic again. So right here on the schematic, you can see the whole point on the idle current is just basically to keep these output devices turned on. So some current is flowing through the output stage at all times. So it's also known as a bias voltage. So it's just, biasing the output devices on a little bit. Now, the whole reason for that is that if the output devices aren't biased on at all or not enough, you'll get what's known as crossover distortion. So imagine if this is the 0 point on the waveform, and the sine wave goes up to the positive peak and then through the 0 point into the negative peak. When it crosses through, it should be a smooth transition from the positive to the negative. And if you don't have the correct bias voltage, or it's missing altogether, you'll get a step in the waveform. So it'll go up, come down, flatten off, and then go down, which is again known as crossover distortion. So of course that's very audible, especially at low volume levels, so you don't want that. And again, if you see that step in the waveform, you know there's a problem with either the bias voltage generator circuit or the adjustment is far too low. So definitely a clue as to a problem in the output stage or an adjustment issue. Now, if it's adjusted too high, meaning that there's too much current flowing all the time, then the output devices will run very hot. And of course, it's wasted heat, wasted energy, but in extreme cases, it can damage the output devices or cause the amplifier to go into thermal shutdown. So of course, again, not desirable. And just going back to the schematic, you might notice that there's some additional complexity, related to these adjustments here, these potentiometers that set the bias voltage. And the reason for this complexity, without going into all the theory of operation, is just to keep in mind, transistors can go into thermal runaway if they're not controlled correctly. So part of the purpose of that bias voltage and what's known as the bias voltage generator is to control the output devices so that the hotter they get, the bias voltage is actually lowered so that they don't go into thermal runaway. Because again, as they get hotter, they're conducting easier. So if you don't have the correct control in the bias circuit, the hotter these devices get, the easier they conduct, more current goes through. That causes them to get hotter and in turn more current, and it's just an endless loop. And again, they go into thermal runaway. So it's very critical that the bias voltage generator and the related circuitry is able to hold the bias voltage stable. And it basically does that as a feedback loop so that it's able to sense the temperature on this heat sink. And you'll notice on the side there's two small transistors. Those are part of the bias voltage generator. So they're basically offsetting that temperature change and correcting the bias voltage. All right, now that the idle current adjustments have been set, the next thing to take a look at is the ISC circuit adjustment. Now, ISC stands for Impedance Sensing Circuit, and it's a proprietary circuit that NAD created, and they use it in a number of their amplifier models. And the ISC circuit forms the basis of what they call the Power Drive. So the Power Drive system is a trademark name, and you'll see it on the front of their amplifier models. It'll say PD, so again, that's Power Drive. Now, later in this video, I'll go through the ISC circuit and the Power Drive system and explain how it actually functions. I think you'll find that useful if you ever have to troubleshoot one of the amplifiers that uses the Power Drive system, and you'll understand better how that all works. Now, the ISC circuit adjustment has to be done after the idle current adjustment because the voltage reading that you get at a test point will be influenced or affected by the idle current. So if the idle current is set higher or lower, then that other voltage that we're going to measure here in just a minute will change. Now I found that the adjustment was quite a ways off in this amplifier. Someone may have tried to adjust it previously, I'm not really sure. But the adjustment itself is quite simple. So you want everything to be stabilized, the amplifier should be turned on and warmed up. Again, the idle current has been set, so everything is in place. You need an accurate digital multimeter, something that can read down into the millivolt range. There's two test points in this amplifier. They're over in this corner right here. They may be in a different location in a different model. But on the two test points, what you're supposed to do is make the voltage equal at each test point. So one of them is the reference, which I'm clipped onto right now. So this test point is just on ground. It's on the speaker ground connection over there, same as chassis ground. And this probe is clipped onto that test point, which on this amplifier, it's TP11. And you can see it's 9.488 millivolts, so almost 9.5 millivolts. So the other test point should ideally be that value. Now, I have found that the other test point, even though when you set it, it kind of hunts around a little bit. Again, the idle current will have an effect on that, and the idle current is always fluctuating just a little bit as well. Also, you don't want any inputs connected or any outputs connected on the amplifier when you're doing this test because that would drastically change these voltage readings. All right, so I'm going to move this test probe over to the other point right here. So you can see it's saying 11.4 millivolts, so a little bit high. Now, just before I started the video, I had adjusted that and it was sitting very close to 9 millivolts, so it's drifted up just a little bit now. So I'm going to keep monitoring it, and the adjustment is right there on the circuit board, and I'll just keep dialing that in and try and get it as close as possible and let it stabilize, very close to that other reference voltage. But again, it seems to be quite touchy. Just a little adjustment on that trimmer potentiometer makes quite a change. But again, I'll keep adjusting that, and it's really important that the ISC adjustment be correct because it influences how that circuit functions, and it'll make more sense when I explain on the schematics how the circuit actually works. But again, it is quite touchy, and again, you do want it as accurate as possible. Keep in mind that line voltage variations will also affect the readings. If the line voltage changes, the idle current will change, and then this sort of idling point of the ISC circuit will also change as well. So you kind of want an average. That's what it really looks like. They don't give a range. They just say make them equal. But in reality, I think it's, make it as close as practical, but I don't think they're ever going to stay exactly equal. All right, the next adjustment to check is known as the minimum volume adjustment. So if we look at the circuit board right here, you can see there's two trimmer potentiometers, so the left channel and the right channel. So what you want to do is set those trimmer potentiometers for the lowest output level at the speaker terminals. So the speaker terminals are not actually connected to any speakers or a dummy load. But what you want to do is input on one of the audio inputs. I'm using the CD input for this test, but you could use any of the inputs. You need to input a 1 kilohertz 5 volt RMS signal. Now the frequency is not super critical, but 1 kilohertz is a pretty standard frequency to use during testing. And yes, 5 volts RMS, not 5 millivolts, not 50 millivolts, 5 volts RMS. It's a very high level signal, but it won't hurt the amplifier, and it's needed for this test. Now, you also need to keep the bass and treble, in their center detent positions. Balance is in the center, and volume is set all the way down as low as possible. All right, so let's go over to the oscilloscope, and I'll show you the result. All right, so channel 1 is connected to the left speaker output, and channel 2 is on the right speaker's output. So the green trace is channel 1, and the blue trace is channel 2. So you can see the vertical scale is set to just 20 millivolts per division. So these are very low-level signals. You can see the readout, channel 1, about 3 to 4 millivolts RMS, and channel 2, about the same. So they're hunting around just a little bit because we're DC coupled on the scope, and we're actually seeing the effects of the DC offset on the amplifier as well, which is also very, very small, but at these sensitive settings on the oscilloscope, it becomes apparent on just little wiggles and movements on the trace. But again, on this adjustment, those two adjustments on the circuit board, those two trimmers, you want to adjust those for the lowest possible amplitude on each channel. And what you'll find is that there's a center null, and then the signal will get a larger in amplitude from each side of that center null. So you're just adjusting for that lowest point on each channel. You could also measure the output with a very sensitive AC voltmeter, something that can read down into the millivolts RMS. The digital multimeter I'm using for these tests could certainly do that, and other meters could as well. But Using the oscilloscope, it's nice because you can just have that visual reference. You can see, the effect of the trace going up and down in amplitude when you're making the adjustment. And you can overlay the traces and have an idea if they're both the same. And if I do that here, if I just move the position of this one down like so, so you can see when the two traces are overlaid, they're basically identical, meaning that both channels are behaving the same way. So that looks very good. So again, you're just adjusting for that lowest point, basically the null. And keep in mind, this is with a 5 volt RMS input, and it's basically just a very small signal that's able to still leak through and create this output. If you put a normal signal in, like say something between 100 millivolts RMS to 500 millivolts RMS, typical audio unbalanced signal level, then this would basically drop away. In fact, I can do that. I'll just change the signal generator right now. I'll go to, let's say, 500 millivolts RMS. Okay, there you go. So that's 500 millivolts RMS, and you can see there's nothing coming out now. In this amplifier, there's no adjustment for the DC offset voltage on the speaker terminals. Now, ideally, it should be 0 volts, but in reality, it will always hunt around a little bit in the very low millivolts or even microvolt range. Now, again, there's no adjustment for that, so if you do have an excessive DC offset voltage, like we did in the part 1 video where you saw it was actually tripping the protection circuit, it means there's a circuit failure because it's not adjustable. It's actually controlled by an op-amp on each channel in what's known as a servo circuit, basically a type of feedback. It's monitoring the output at the speaker terminals and then putting an offset voltage around to the input stage of the power amp, and then it's just correcting for that offset voltage. So there's nothing to adjust, but we can check it, and it looks very good. You can see right now on the left channel over there how low that value is. So it's sitting down in the microvolt range at times, and then comes up to maybe 1 or 2 millivolts and then goes right back down. So that's perfectly acceptable. Notice it's a negative voltage, and offset voltages can be that way on the speaker terminals, that sometimes they are positive, sometimes they lean more towards a negative voltage. That's not an indication of any kind of a problem. So no problems there on the left channel. Let me just move the probe over here to the right channel. Take a look at that. I don't need to move the ground probe over because the ground connection is the same negative connection on the speaker terminals, is all common, chassis ground and everything, so there's no need to move that probe. All right, and we can see on the right channel, no problems there either. So maybe within a millivolt higher than the left channel, but perfectly acceptable. Not an issue whatsoever. All right, let's do a full power output test on the amplifier. So this amp is rated 80 watts per channel continuous into either 8 ohms or 4 ohms, so we want to make sure that it can meet that specification. So I'll do the test into 8 ohms first, and then I'll do a 4 ohm power test as well. So for the 8 ohm test, these are 8 ohm dummy load resistors. They're just connected to the speaker terminals. And on the 4 ohm test, I'll parallel these with an additional 8 ohm resistor on each one. So you can see the oscilloscope is connected to the speaker outputs, and the input right here is coming from my signal generator. It's set to 1 kilohertz with a 500 millivolt RMS signal level. Now, you don't want to use too low of a signal level going into the amplifier. Let's say this was just maybe 50 millivolts, something very small. You would probably end up turning the volume control all the way up and not be able to achieve the full output power. So 500 millivolts should be perfectly fine. All right, I'll move you over to the oscilloscope and let's take a look at the results. Also, I have the soft clipping circuit turned off right now because we want to see when the amplifier absolutely clips and we know we've hit the limit. Then I'll turn the soft clipping circuit on and we'll look at the result and compare. Remember, all the active components were changed in that soft clipping circuit on both channels, so we definitely want to make sure that that's working correctly. All right, here we are back at the oscilloscope. Same as before, channel 1 is on the left channel, channel 2 is on the right channel. So the green trace is channel 1, blue trace is channel 2. Now it's set to 20 volts per division on the vertical scale, so much larger voltage levels. So 80 watts into 8 ohms is 25.3 volts RMS. So we know that when we hit that voltage level that we are achieving that 80 watt output. All right, here we go. Let's see what happens. So about 6 volts, both channels look to be very close in the same amplitude. No problems so far, looks very good. Okay, there's clipping, and looks like both channels are hitting that clipping point at the same time. So when that signal clips, that's the absolute maximum. So let's take a closer look at the voltage levels right when that was clipping. I would say right about there, and we have, it looks like 26.2, 26.5 volts. And again, 25.3 volts would be 80 watts. So we are hitting that 80 watt level on both channels. So no problem. Looks like the amplifier is working very well. So I'll switch the resistors around and reconfigure them so we have 4 ohms, and let's do the same test. All right, let's try the full power output test into the 4 ohm loads. So I actually found 4 ohm power resistors, so I didn't need to parallel additional 8 ohm resistors with the first resistors that we were using. That worked out better. It's just less test leads and jumper wires to have to connect. Okay, here we go. Now, 80 watts into 4 ohms is 17.89 volts RMS. So let's start to increase the volume. All right, that looks good so far. 12 volts right there, 12 volts RMS, 13. And it's starting to clip right there. You see that it's flattening off. So I'll back off a little bit. So right there, that looks like that's right before the clipping point. And again, it would be 17.89 volts, and we're seeing 18 volts and some change on both channels. And both are reading very, very close. So no problems, that looks fine. It's definitely outputting the 80 watts into the 4 ohm loads. So very happy with that result. So as I already mentioned, the soft clipping feature was turned off for these power output tests so that we could see when the waveform actually clips, have a good idea of the absolute maximum output power from the amplifier. But I want to make sure that the soft clipping circuit is working correctly given that all the active components in that circuit were replaced. So again, if I increase the volume level with the soft clipping feature disabled, we hit that point where it goes up like this, and you get that very harsh clipping where it flattens off. Now, if you were actually listening to music and had this connected to speakers and the waveform were to clip like that, first of all, you'd be driving the amplifier extremely hard. It'd be very, very loud output levels. But that clipping point is basically like a DC voltage at that point where the waveform just flattens off. And that's very hard on speakers. You'd very likely damage the speakers. It's hard on the power amplifier because the current levels at those points rises up. So it's just not good all around. And the soft clipping feature should round off that waveform and help to prevent those very harsh clipping points. All right, so I'm going to go ahead and flip that switch over to the soft clipping feature, and let's try this again and see how the waveform looks. All right, so the soft clipping feature is now enabled. The front panel LED is turned on. It's still connected to the 4 ohm dummy loads, but that doesn't matter. The soft clipping works no matter what the impedance is. So we'll increase that. Yeah, and look at that. So you can see how it rounds off the waveform. So eventually it does flatten because it just can't drive the output. But that initial point where it starts to hit right there, you have a little bit more rounding on the waveform instead of that harsh flattened off tops and peaks and valleys in the waveform. So yeah, I would say the soft clipping feature is working the way that it's supposed to. That looks very good. So that would definitely help to prevent that horrendous distortion if the amplifier were to be driven, extremely hard. So looks like that's working perfectly fine. And just for completeness, I'll do the soft clipping circuit with an 8 ohm load on each channel. So the soft clipping circuit is turned off right now, but I've switched it over to 8 ohm dummy loads. And so we can see the output level here. Just get a higher voltage because it's into 8 ohms instead. And there's our clipping. So very harsh clipping at that point. Okay, now I'll go ahead and switch on the soft clipping circuit. All right, soft clipping is enabled. Let's try it again. Yeah, that rounds off nicely there. So it's not such a harsh clipping point. So yeah, it looks like the signal is being clipped the way that it's supposed to, and the circuit is definitely working correctly. So very happy with that result. So the next thing that I want to do is check the frequency response of the amplifier. So to do that, I'll use my Hewlett-Packard 3585A spectrum analyzer. So this is an older model spectrum analyzer, but I really like this model. It has some very useful features on it. It's great for use on audio work like this, as well as RF work. Now it only extends to 40 megahertz, but don't let that fool you. It's still very useful. So one of the things I like about it is it has a 1 megohm input in addition to a 50 ohm and a 75 ohm input. So this is connected directly to the speaker output on the right channel, and it has a tracking generator built in. So the tracking generator is a 50 ohm output, and that's terminated into a 50 ohm feed through right here, so it does see a 50 ohm load on the tracking generator, but then the output goes into this Y splitter, and then I have this RCA cable connected to the left and right inputs. Again, we're only looking at the right channel. I'll repeat this test on the left channel. I won't include that on this video unless there's any issues going on the left channel, and then of course I will include it and we'll certainly address that. But if the left channel checks out the same as the right channel, then again, I'm not going to include it. So if you're not familiar with a tracking generator, as this is sweeping the frequency range, so this is going from 20 hertz to 30 kilohertz, this tracking generator is following that sweep. So basically it's putting the signal into the amplifier, it's passing through, the tone controls are all in the 0 or defeat position, and then it's coming back out on the amplifier's speaker outputs and going into the spectrum analyzer. So the end result is that we see this flat line, and that's exactly what we want to see. That means that the frequency response of the amplifier is flat. And that's a very good sign. Again, that's what you're looking for. So you don't want a frequency response that has, peaks and valleys and, some end, like say the treble is up or down, because that's going to color the sound. So, again, this flat line is exactly what you're looking for. Now, on the actual spectrum analyzer display, the top graticule over here on the very top line would represent a 7.08 volts, so just a little over 7 volts. And the actual measurement, I don't know if you can see it on the camera, there's a little dot right here on the trace, and that's actually right at the marker, and it's at 10 kilohertz. And this line right now is sitting at 1 volt or 1,000 millivolts, which is what it's showing right up there. So that's the actual output that's coming out of the amplifier right now. And I do have it terminated on an 8 ohm dummy load, but anyway, that's actual speaker output voltage right now. So you can move this marker around. If I go all the way up here, I'll just go all the way to the end. So the marker is right on the end over here. So that's 30 kilohertz, well above where the amplifier would normally work. And it's sitting at 988 millivolts. So, only down just a tiny amount, not a problem whatsoever. If I come back over here, sitting right there at 20 kilohertz, it's also at 988 millivolts. And if I come down right there, it's sitting back at 1,000 millivolts or 1 volt. And that's 15.5496 kilohertz. So again, looking very flat. That's very, very reasonable. And if I change the scale, those numbers and measurements might zero in and change just a little bit as well. But I'm not going to get into all of those types of detailed measurements in this case, because there's really no problems. It's looking perfectly fine. But one other thing that I wanted to mention, that if you are doing this type of a measurement, this is not a logarithmic sweep. Okay, this is a linear sweep going across. So if I take the treble control and I turn it up right now, okay, so now the treble is boosted all the way to its maximum, or if I cut the treble all the way down, okay, you can see it definitely has an effect, and it's what we would expect. You're seeing the change from the lowest frequencies down here, something above the very lowest point, a little bit there. You can see kind of changes right there, and then everything up there is changing, up or down as I move the control. So no problems there. Now if I go to the bass control, and right now I just turn the bass all the way up, and I turn the bass all the way down. And you can see it just causes kind of a wiggle over here on the end, but it looks like almost nothing's happening. And you might be thinking, well, it's not working correctly. Well, no, because the way audio frequencies work, if it's not a logarithmic scale, then the lowest frequencies are all scrunched over here on the left-hand side. We can change that, but you actually have to do, if you can do a logarithmic sweep perfectly fine, this can't do that. So what we need to do is change the stop frequency. So the start, again, is at 20 hertz, but I'll change the stop frequency to 1 kilohertz. Okay, now the sweep is much slower, so we'll just let this go across here, and it's going to update. We'll just give it a moment here. The sweep time was much faster with that wider frequency range that I had when the span was wider. Okay, so it's completed the complete sweep now, it's done. Now I'll go here and change the base, and I'll go ahead and turn the base all the way up. Okay, so now give it a time to do another sweep and see what we have. Now we can see that it does in fact increase those lowest frequencies. So I'll go ahead and move the marker down here. And you can see there's a definite increase here. You know, it's a 1 volt without the base, you know, being boosted up, but now it's 2.26 volts, so a definite increase in the output, and that's sitting at 112 hertz right now. I go all the way down there, there's sitting at 20 hertz, 2.62 volts. As we come down here, start to level off, and go all the way over here. It's 1.03 volts out there at 925 hertz or so, and that makes perfect sense because typically the base control is not going to be boosting frequencies much above 1 kilohertz. So you start to get to 1 kilohertz, you're in the mid-range frequencies anyways. So you know, again, this is working perfectly fine, exactly what you'd expect to see. So if I roll the marker down here a little bit lower, you can see it starts to come up. Here's 1.5 volts right there at 289, 290 hertz. So again, the frequency response looks perfectly fine, not seeing any issues whatsoever. So the next thing that I want to cover is some details about the ISC circuit, that impedance sensing circuit, and the power drive feature that these amplifiers have. All right, so let's take a look at the ISC, or impedance sensing circuit. Again, this is the circuit that NAD's trademarked power drive is based on. It, you know, it forms the control and the whole idea behind that power drive idea. So I have quite a bit set up here. I'll explain exactly what's going on. So I'm using my fluke scope meter so that I can have the oscilloscope and the digital multimeter in the same shot. I think it'll make things a little more clear. And I have my signal generator set to 1 kilohertz, 500 millivolts RMS, and it's driving both the left and right channel. It's connected back here. You can see the 2 8-ohm dummy loads. They're connected to the left and right channels. And I have the oscilloscope connected to just the right channel, so just to simplify things, we don't need to monitor both channels, but both channels are being driven. If I increase the volume, you can see some output right there on the right channel, but if I go over here to the left channel, there's the left channel's output. So again, both channels are being driven. And we're going to start with the 8-ohm dummy loads, but then I'll switch over to the 4-ohm dummy loads, and you'll see a key difference, and that's really when that power drive idea comes in. Okay, so now the digital voltmeter over here, it's measuring DC volts. And one test lead here is just on chassis ground. The other test lead right here is poked into a little connector, and it's, if you look on the silk screen on the board, it's marked as trigger. Okay, so any of these amplifiers that have the ISC circuit, you're going to see a circuit in this system that's marked as trigger. You also see it on the schematic. So you can see right now, if I turn the volume, you know, all the way back down, no output whatsoever, the trigger is actually sitting at 1.433 volts, so just shy of 1.5 volts, and I suppose in some cases it might rise up to about 1.5 volts, so call it 1.4 volts for now. All right, so now I'll go ahead and increase the output, turn the volume up, and I'm going to take this all the way to clipping right there. So you can see the waveform is starting to clip right there. So we know that that's the full output. That's 80 watts into 8 ohms. So driving it as hard as the amplifier can go. And this is over here at the 3 o'clock position. But take a look at the voltmeter over here. The voltage basically doesn't change. I mean, that trigger voltage is just remaining 1.4, goes to 1.3, all the way up to clipping. Some slight variation there, but very, very minimal, perfectly normal. That's what you should expect to see. So again, if you're troubleshooting this ISC circuit and you need to check that trigger voltage, now you know what the voltage should be. It's not marked on the schematic, so it's a good starting point to know what that trigger should do. And again, this is with an 8-ohm load. All right, so keeping in mind what we're seeing here, I'm going to switch over to the 4-ohm dummy loads, and then we'll see a difference. One other thing I should point out before I do that, I'm just going to move this over from the trigger point, and I'm going to put it on the power supply rail. So this right here, very careful right there. So there's our, it's marked as the 55 volt rail, 52 volts, that's perfectly fine. It's not always right at 55, depends on the line voltage because that's an unregulated supply. So if I turn this all the way up again here, I'm going to take this all the way up to clipping. Okay, right there, and you can see it does sag down to 40 volts. Again, not a problem. We're able to achieve the full 80 watt output, and it's normal that those power supply rails do drop down. So you can see it just drops as the output load is increasing, or it's driving the, I shouldn't say the output load is increasing, but it's driving harder and harder with more output voltage. So there's more power going into the load. The voltage is being pulled down on the power supply rails. But again, perfectly normal. And you can see that the voltage is just changing just slightly as I continuously turn the volume. Okay, so perfectly normal. Just for completeness, I'll go over here to the other rail. So here's the negative 55 volt rail, minus 52. Turn this all the way up. So you can see some decrease. It goes there. There's all the way to clipping, down to about 40 volts. All right, so those are values that are very typical and that you should expect to see. So now I'll go ahead and change this to the 4 ohm dummy loads, and we'll take a look at the result. All right, so now I have the 4 ohm dummy loads connected. Everything else has remained the same. So let's take a look at the result. So the trigger voltage is sitting at the 1.4 volts. I'll start to increase the volume. You can see on the oscilloscope we're getting an output. Slowly increase, and right there, the trigger voltage just dropped to 0, so it went away. Now I'll increase the volume some more, and you can see the output keeps rising, and then right there it hits the clipping, so we know that the output is driving the full 80 watts into the 4 ohm loads, and it's able to hit the clipping point. But notice that that trigger voltage has now disappeared, where when it was driving the 8 ohm loads, it was able to hit the clipping point, and the trigger never disappeared. All right, so that's a key difference. So if we take a look at the volume control, I'll turn this up slowly here just to kind of get a reference point. So right about there. So I would say that's about the 11 o'clock position on the volume control. That just happens to be where it is occurring now because of the input. I'm using a 500 millivolt input. That would vary depending on the input level, but for this particular test, about 11 o'clock is when the trigger voltage changes. So keeping that in mind, that trigger drops to 0, what is the trigger actually controlling? Well, let's go over here to the power supply rail. So I'll go to the negative 55 volt rail. Okay, so we can see it's negative 52, but very close to that value. I'll start to increase the volume, so we're going to get an output on the oscilloscope. 48, 47, and then look at that, 37, so basically a 10 volt drop. And look at where the volume control is. It's right at that 11 o'clock position. So when the trigger voltage falls to 0, the power supply rail changes. Okay? So I'll do that again. Turn this up. 47, 46, and then 37. And if I keep increasing this, we go all the way up here, and drive this all the way up to about the clipping point right there. And it pulls it down to about 30 volts or 31 volts, which is perfectly normal. But you can see there's about a 10 volt drop that suddenly occurs. If I go to the other power supply rail, right there, the 55 volt rail, 52 volts, start to go up here. We get the volume goes up to about that 11 o'clock position, 47, and then boom, 37 right there, jumps down or drops down. And then if I keep increasing this, we'll see the same result. Goes all the way up to clipping right there. Okay, so with those measurements and what we're seeing happen, that's basically what the ISC circuit is supposed to do. It controls the power supply rails to the output stage. And the reason they're doing that is so that under 4 ohm loads, okay, the output of the amplifier still goes to 80 watts, but it doesn't exceed 80 watts. So let's say you didn't do this and you kept the higher voltage on the output devices. In theory, the output power could end up doubling. Now, that actually doesn't happen because there's losses in the power supply rails, drop down and things like that, so you would never see it actually double, but the output power into a 4 ohm load could increase substantially. It could cause overheating conditions and other problems and overloads. So to make the amplifier drive a 4 ohm load to 80 watts or an 8 ohm load to 80 watts, they switch the power supply rail, and that's what the ISC circuit is supposed to do. So we'll look at the schematic and we'll see how this all works, and we'll keep in mind these measurements. and I think it'll all start to make sense. Now keep in mind what you just saw. The power supply rails on the output devices sit at a high voltage and it drops to a low voltage. That's very different than what some other manufacturers do. I've personally worked on a number of Carver amplifiers that have multiple power supply rails, but they start on the low voltage rail, and as the demand on the amplifier increases, it switches to a higher voltage rail. Well, this is just the opposite. It's actually switching down to a lower voltage rail. So there's some misinformation on this power drive circuit about being similar to some of these other amplifiers where they have multiple power supply rails, and it's basically just the opposite in what it does and the purpose of it. All right, so again, keeping all these measurements in mind, let's jump over to the schematics and take a look. And I've broken the schematics down to the different areas within the power supply and the control circuit, and we'll just kind of run through how the circuit works. And again, I think it'll help if you're having to troubleshoot one of these amplifiers and work in the power supply or the control circuit. So let's take a look. So to better understand the ISC circuit, let's start by looking at the power supply rails first. So we'll start with the 55 volt power supply, and we'll look at the low voltage supply. So we know that there's a positive and negative 55 volt rail that goes into the main output stage of the amplifier and some other locations as well. So starting in this corner right here is the main power transformer. So it's just a traditional center tapped transformer. So we have a ground connection right here. That's the center tap. And then we have a 41 volt, 41 volt. So those 41 volt outputs come over here. So you can see this one comes up here, comes over here, and up to the bridge rectifier. And the other 41 volt comes up here into the other side of the bridge rectifier. So coming out of the bridge rectifier, here's the positive side, the negative side. So positive output voltage right here through this SCR, which I'll talk about a little bit later. Notice it's on the anode of the SCR. The cathode is on this side. Comes over here through this current sensing resistor and some circuitry. We'll get back to that. This is a very low value resistor, just 0.05 ohms, 5 watt. So it comes down here and out. So that's the positive 55 volt output. Now on the negative side right here, it comes over, comes down through the SCR on the negative side, but notice this is the cathode, so these are in reverse direction. And then the anode ties in over here from that SCR, and then come over here, and we're off to the negative 55 volts to the rest of the circuitry. Okay. Now the filter capacitors are right here, and you can see each filter capacitor goes from the power supply rail and then to the chassis ground connection. Now, it's very important to notice where those are located in relation to the SCR, because an SCR, if it is turned on and it has a continuous DC voltage, if you trigger an SCR, it'll be locked on. It won't turn back off. But we want to be able to turn these off whenever needed. And I'll talk about how these are controlled in a little bit. But notice that they're actually switching a pulsating DC voltage, because the DC voltage off of this bridge rectifier on the negative side and on the positive side is a pulsating DC. Okay, it comes out, it pulses up, down. Up, down. So when it goes down, it's to 0, pulses back up and down. So every time that voltage drops down to 0, the SCR has a chance to turn off. But if it's re-triggered, then it, of course, stays on. All right, so that's very important. That's how these SCRs can control a DC voltage. All right, so that's the basic layout, for the 55 volt rails. Pretty straightforward. If we look down here, there's some other auxiliary circuits going on down here. I won't get into a lot of details, but you can see there's another bridge rectifier here, and this is marked as plus 55 VA and minus 55 VA. This is an auxiliary 55 volt supply, and this second 55 volt supply, it doesn't change. Obviously, there's no switching. It's very traditional. The output is coming over here to some filter capacitors, and it goes on out. Over here it's plus and minus 55 VA. Again, and that goes to an auxiliary circuit and is regulated. So this has nothing to do, with the 55 volts that we've been talking about. Down here, there's a switching supply right here, very traditional, very simple switching type supply. We can see the optocoupler for the feedback, the transformer right here. So this gives us the isolation, AC line coming in, bridge rectifier, some filtering, the control chip right here. So very traditional. This is a standby circuit, and I believe it's, it's providing a 5 volts for standby voltage. This diode right here and this resistor, I believe that's coming over here. Yeah, that's the AC detect. I believe that goes to the protection chip so that it knows for a delay on power up. Some additional auxiliary circuits down here, just bridge rectifiers and very traditional linear type power supplies, voltage regulator chip. So pretty straightforward on the rest of it. AC line switching over here, auxiliary outlet, and so forth. Okay, so now let's take a look at the lower voltage power supply. So this is the plus minus, it's about 38 volts. I made a mention here, it's roughly 38 volts. It's very hard to test this power supply, of course, with the amplifier all assembled and getting into the power supply board. It's very compact and I couldn't get to the bottom of the board to make any measurements. So this is a best estimate of what this voltage would be. We saw it drop to 37 volts, but when we're seeing that just previously when I was showing you that, that's actually loaded, because the amplifier is working at that point. So I'm not really sure what this value would be if that circuit were to be unloaded. So it's about 38 volts plus minus, but that's of course under load, and that's probably how you would end up measuring it anyways, if you're doing troubleshooting. But taking a look over here, starting with the same transformer, we have the lower voltage taps the 32 volts over here, okay? And again, it's using that same center tap that goes to chassis ground. So the 32 volts comes over here, and now we're using this other bridge rectifier. So the AC line comes up here to the bridge, the other side right here, and then we have the positive of the bridge and the negative of the bridge. So the positive output comes over here. Now we're on that same filter, main filter caps that we saw before. Comes over here through that current sense resistor and off. And then the negative side right here comes over here. There we are on the other filter cap and off. Now you might be thinking, well, wait a minute, we've got, two conflicting voltages. Why doesn't it backfeed, or why don't they interfere? Well, if you look right here, let's look at the positive side. The negative side works the same way. If the positive output comes over here and it comes up, but if this SCR is turned off, it cannot flow back this way. And likewise, when this turns on and it puts a higher voltage out, that higher 55 volts cannot flow back because you have a positive 55 coming here, but look where you're at on these two diodes. You're on the cathode of both diodes, so you won't get any current flow back into this bridge. So essentially, the two power supplies don't interfere with each other. All right, so very straightforward circuit, very traditional in design, particularly on this low voltage rail. So basically the low voltage rail is sitting here all the time, sort of ready to work, but the 55 volt rail basically takes over most of the time. All right, so moving on to the next schematic here. All right, so let's take a look at this current sensing portion of the circuit. So right here we have this very low value resistor, and essentially you get a voltage drop across this resistor, and the voltage drop increases as more current flows. So some additional circuitry right here that's part of that monitoring, but what ends up happening is that you have about 0.9 to 1 volts that comes out of here and goes off to the ISC circuit when it triggers to the low voltage rails. All right, so it's about 0.9 to 1 volts when that trigger happens. So this is an input to the ISC circuit. Very important. It has to know what the current is on this power supply. Now they're only monitoring the current on the positive 55 volts because in normal operation, the same current is flowing on the negative 55 volt rail. So they chose just to monitor the one power supply rail. Now remember that I mentioned when you set the idle current, you have to do that first because that influences that adjustment that's on the ISC circuit. And the reason is the idle current is flowing through this resistor. So let's say the ISC circuit was all adjusted and then you went back and changed the idle current setting and maybe you increased it. Well, then you have more current flowing through this resistor and then this value increases and then that adjustment on the ISC circuit is no longer correct. Remember the two test points that had to be made the same value. All right, so that's why this circuit right here is, everything is being powered off through this positive 55 rail. It's in the output stage and other portions of the amplifier. So if there's a change in any of that, it's going to change this sensing right here and the value that's created, this voltage on here. Okay, so moving along. All right, so here's the ISC circuit. So we'll start by looking at the inputs and the adjustment of the ISC. So down here you can see I marked it as right and left. So these are the right and left outputs of the amplifier. So these are going to the speaker relays and off to the speaker connections. So we have two diodes right here, and they're on each of the output channels. And essentially what they're doing is they're just monitoring the voltage on the output, rectifying it, bringing it up here through these resistors, and it's being combined. So you have a summed voltage over here. And it's coming up to this op amp. And this op amp and also this op amp are being used as comparators, meaning that the output is either high or low. So the other side of this op amp is between two resistors. So we have a voltage divider. You have 18 volts right here, and then through this resistor, a voltage at that midpoint, another resistor right here, and that goes to the chassis ground. Okay, so this is essentially comparing this input against that input. Now, the other op amp right here, here are those two test points that we had. So test point 11 is what you measure, and you want to make test point 10 the same as. So on this one, you can see this voltage that's developed off of the output of the amplifier also comes over here, comes into this op amp. And then here's that adjustment for the ISC circuit. So it's another voltage divider. You have positive 18 volts, chassis ground. So you have a movable wiper right here. So you have a voltage divider, comes up here. And then that, as you're varying that, changes that voltage that you end up measuring at this point. Now notice there's a 10 microfarad capacitor right here, and when you make this adjustment you'll notice there's some settling that has to occur at this point, and you have to let that kind of drop down if this capacitor has a charge on it. So it does take a little bit of time. All right, so taking a look over here though, that's not the only input to this side. If we look up here, this line comes over and we see that IV line right there. So this is from that current sensing input. So that's why this point right here, test point number 10, is affected by the adjustment of this potentiometer, but also by any current that's flowing in the amplifier. So again, that idle current comes into play. If you make a change on the idle current, then that's going to change that current sensing, and it's going to change the voltage that you end up measuring at test point number 10. All right? All right, so here's the ISC circuit's trigger output and also the temperature trigger. So we can see, again, the same two op amps that we were just looking at. These are the output side, so it's combined together, and then you can see it comes up over here, and that's the ISC trigger, and we saw that 1.4 volts that we're measuring. So when it's pulled low, it turns the 55 volt rail off, okay? Now there's another control that can occur on this ISC trigger, and that happens right here. You can see that there's this temperature sensing resistor. So essentially this line can also be pulled low, and we see a path right here through this diode, through this transistor, and then to the ground connection. And this transistor would be turned on when this, you have a voltage divider on the base right here, when this hits 80 degrees Celsius. And when that happens, it's such that this transistor would conduct, and again, it will pull this line low. So don't confuse this temperature resistor with the protection or the fault temperature sensor. Okay, there are actually two temperature sensors on the heatsink, and the other temperature sensor, I believe, trips at 90 degrees Celsius, and that's the final shutdown, that if it hits that point, the protection circuit kicks in. So what they chose to do is have this one trigger just a bit sooner at 80 degrees Celsius, and basically if the heatsink is getting extremely hot, what they want to do is back off the power supply rails and lower them down so that hopefully the amplifier keeps working and it doesn't just completely shut down. So that's a nice feature, because it basically, it's able to step in and sort of preemptively protect the output stage from overheating in a drastic way by lowering that voltage down. And then of course, if the temperature recovers, then this would go back to normal operation over here. So if you see this trigger happening unexpectedly, you might want to take a look at this portion of the circuit. Don't forget that this can affect that trigger circuit. So going back to the power supply schematic, here we are back on the trigger voltage right here. And again, remember it was 1.4 volts, and that was high. So when it's 1.4 volts, the 55 volt rails are turned on, which is the way that the amplifier just sits and idles, that they're always on. So we know that this should be 1.4 volts all the time, unless things are happening that cause it to need to go to that lower voltage rail. So when you have 1.4 volts coming in here, basically we have a transistor switch right here, and essentially there's an NPN transistor here and a PNP transistor up here, and what this is doing is turning on this transistor and this transistor. And you can see that there's a path right here on this SCR. So you have the gate of the SCR coming down here, you have this transistor and a resistor coming back around over here. So that's able to control this SCR. Same thing over here, you have the gate, this resistor through this transistor and back down again to the anode of the SCR. So you're able to control the gate on each of these SCRs with this high voltage that's coming in, the 1.4 volts. Okay, when I say high, I just mean it's a higher level, 0 or no voltage being the low level. So this is not, of course, a logic level. I don't know why they settled on 1.4 volts. It must have to do with the rest of the circuit and how it functions over here. But nonetheless, those are the correct values to read, 1.4 volts or 0 volts. Okay, so looking at the other way that the power supply ends up working is when we have the low voltage rails. So that happens when this is at 0 volts, okay? So 0 volts, the 55 volt rails are turned off, okay? And when that happens over here, this NPN is off, the PNP is off, and these SCRs are no longer conducting, and then the power supply is essentially on this other bridge rectifier, and it's blocking or not allowing the 55 volt output to be used. So I hope you found the information useful on the ISC circuit. If you have to troubleshoot one of these amplifiers and the problem is related to the ISC circuit or the power supply, hopefully this will give you some basis on where to start doing some tests and some actual voltages and things that you could measure. So this concludes the troubleshooting and repairs on the NAD C356BEE stereo integrated amplifier. So I'm very happy how the repairs turned out. The amplifier is performing very well. I'm looking forward to putting many hours of listening use on this amplifier. I think it'll be a pleasure to listen to. So if you did enjoy this video and following along on this repair adventure, please give the video a thumbs up. It definitely helps it on YouTube, and it lets me know that you enjoyed the video as well. And if you're enjoying the videos on this channel, don't forget to subscribe. There'll be many more videos coming up in the near future. Lots and lots of projects in the queue. You won't want to miss any of that. So tap that bell symbol to be notified when I do post a new video. And as of making this video, the channel has just totaled over 5,000 subscribers. So I just want to take a moment and say thank you to everyone who has subscribed. It means a lot, and I'm happy to know that you are enjoying the content that I put on this channel. All right, until next time, take care, and goodbye for now.